Section 1.6 is limits involving infinity. And up to this point, we've seen maybe a couple limits involving infinity. In other words, a limit that might have trended towards infinity as x approached to number a. And we possibly even looked at a limit as x approaches infinity and what the output of that function value might be or might grow towards as x approaches infinity. So to introduce maybe a slightly more formal definition of this, again, this is just the intuitive definition of a limit at infinity, but it'll serve our purposes. This notation, the limit as x approaches a of f of x equals positive infinity, means that the value of f of x can be made arbitrarily large, in other words, as large as we like, by taking x sufficiently close to a. This is on either side of a, but not equal to a. So in other words, we can pick x values that are closer and closer to a in order to drive our function value up as large as we like or may be required to. So there's also a precise definition similar to non-infinite limits, and maybe we've seen that in previous examples or in meetings, or maybe not, but for now this will suffice. Note that there's also a similar definition for negative infinity, where we're driving the function values f of x into arbitrarily large negative values rather than positive values. So one function we've probably already had a look at is this, one quick example, the function 1 over x. And we know that at x equals 0, the function y equals 1 over x has a vertical asymptote. So if we take x values that approach 0 from the right, that's moving along this x-axis towards x equals 0, that vertical line there, which is our vertical asymptote as we know, we realize that the y values of the function grow upward in that direction, right? So this thing is trending towards positive infinity. And you could probably convince yourself of that. If I said, can you find a number that's close to 0, but to the right of it, that makes the function 1 over x larger than 10,000, larger than or equal to? Well, then you'd say, okay, 1 over 10,000 is a number in here somewhere really close to 0. And if I do 1 over 10,000, right? If x is the number 1 over 10,000, and I'm dividing 1 by 1 over 10,000, then my output's going to be 10,000 on the right. So I'm able to make this function as large as I like by picking an x value that's closer and closer to 0. Okay, so that's sort of our intuitive definition at work. Similarly, on the left-hand side, as we approach 0 from the left, from its negative side, right, or just its left side, we notice that the y values of this function trend downward towards negative infinity, and we could play the same game with something like negative 10,000, or negative 100,000, or negative 1 million, and we'd find negative 1 over 1 million, which is a pretty small decimal. We plug that in, and then 1 over negative 1 over 1 million would be negative 1 million, and we get an arbitrarily large negative value on our function by getting x closer and closer to 0. So that's the game there, and hopefully that's enough to kind of get a feel for these. We're going to have a couple rules that'll help us calculate these more cleanly. Let's have a look at some more examples. So we're asked to evaluate the limits of these two given functions. Notice the second one we've actually already done. Maybe if you want to convince yourself, you could put a table together, right? X and f of x, and then put some values down and see how all that comes out. But if you're convinced, then we can just leave that as is. Let's have a look at 1 over x squared as x approaches 0. So what I would encourage is if the function's got a vertical asymptote where you're asking, or where you're being asked to find its limit, you would probably be best off to consider its each of its one-sided limits, because they might be different, right? Remember, in this case, as we approach 0 from the left, it's negative infinity. If we were to approach 0 from the right, we'd get again that it's positive infinity, so they're different. So, you know, not only do each of these one-sided limits diverge, they just diverge in different ways. So there's no two-sided limit in this case. So for 1 over x squared, let's see whether or not it has a limit. Well, we could do this by table if we wanted to convince ourselves, or just think about if I plug in values that approach 0 from the left, they're getting closer and closer to 0, something like negative 1 over 10, negative 1 over 100, negative 1 over 1,000. If I plug those in for x, those are numbers in the denominator. So maybe negative 1 over 10, when I plug it in for x, I get negative 1 over 10 squared. That's positive 1 over 100. And that's 1 over 1 over 100. That's 100. So those values are getting arbitrarily large, and they're positive. Even though I'm plugging in a negative number, the square corrects the sign or makes the sign positive, and we're trending towards positive infinity. And if we do that from the right of 0, we see that it also trends towards positive infinity. So what we can say, in some sense, since the one-sided limits both diverge, but they both diverge in the same way, we can summarize all this information as saying this thing does have a two-sided limit that diverges to positive infinity, right? So still, it doesn't, the limit diverges because it's going to infinity. It's not a real number. But since both the left-hand and right-hand limit trend towards positive infinity or equal to positive infinity, then we could just summarize all the information by saying the two-sided limit is positive infinity. And remember that the graph of this function looks something like this, heard it referred to as the volcano function by students, right? As we move towards 0 from the right, it moves up towards infinity. And as we move towards 0 from the left, the function trends towards infinity. And there's our 1 over x squared function. So let's keep going. So vertical asymptotes, right? Now we're finally in a position to define a vertical asymptote, even though we already know what they are from algebra, and we've been using them to help intuitively deal with these functions. So vertical asymptote is given by any one of these 6 conditions down below. So if x approaches a, as the limit as x approaches a of f of x is equal to positive infinity, a two-sided limit is infinite, then the function has a vertical asymptote. If the left-hand limit of f of x as x approaches a is infinity, f has a vertical asymptote. So on and so forth. Same for negative infinities, right-hand limits. Anytime we have an infinite limit, we're dealing with a vertical asymptote. Because what that's saying is that the y values are moving up towards infinity, one way or the other, from the left or right, or they're moving down towards infinity from the left or from the right, or both. Right. So we know then, if we look back real quick, that 1 over x squared clearly has a vertical asymptote at x equals 0. Right. And the function trends towards positive infinity. So both those sides are moving up towards infinity from the left or from the right. So there's a case in point for this definition for vertical asymptotes. Again, that should be no surprise, but now we're connecting the definition of vertical asymptote to limits of functions. So determine the left and right-hand limits of the function tangent of x at its vertical asymptotes. Okay, so remember that tangent, let's just take a quick moment to think about tangent before we just accept this as fact. Remember that the tangent of x, and I think I might have pointed this out in a previous lecture video, but nonetheless, it doesn't hurt to have another moment with it. We're worried about division by 0 because tangent of x is defined as sine of x over cosine of x. Well, we're worried about places where cosine of x might be 0, right? So it has vertical asymptotes, if you recall the graph, and the vertical asymptotes occur wherever its denominator function, cosine of x, is equal to 0. Well, if we think back, we know that cosine of x is equal to 0 whenever x is pi over 2, or 3 pi over 2, or 5 pi over 2, or so on, right? And so this is where I could add possibly plus k pi, right, where k is any integer. And I might have written that in a different way previously, but I think this does just fine. This will work as well. When k is 0, we get our first vertical asymptote of pi over 2, or what's thought of as one of our first vertical asymptotes. When k is -1, we get pi over 2 minus -1 pi, and that's negative pi over 2. That's the left-hand side of our principal cycle. And we'll get 3 pi over 2, negative 3 pi over 2, 5 pi over 2, and so on by scrolling through all these values. So let's just look at one of these places where we have a vertical asymptote. We're just going to look at pi over 2. So we'll look at pi over 2 as x approaches it from the left. We'll look at pi over 2 as x approaches it from the right. And we know that Of course, tangent of x has vertical asymptotes. We recall its graph from trigonometry. So what we see here is the following. We have the limit as x approaches pi over 2 from the left, and I've got tangent of x, but I'm not quite sure how that behavior is going to look. I could refer to a graph, but that's kind of cheating. Maybe we want to use this information to help reconstruct the graph of tangent, or inform us to construct the graph. So maybe I rewrite tangent again as sine of x over cosine of x, right? So as we approach pi over 2 from the left, say we start around 0, right? It doesn't matter exactly where we start, but we can start somewhere arbitrarily close to pi over 2. If we start at 0 for x, and then take maybe pi over 6, and then pi over 4, and then pi over 3, we can think about, we're approaching pi over 2 from the left-hand side, right? Remember, treat this as a number line. Don't think of it as the unit circle necessarily. So if we're at 0, and then pi over 2 is here, before we get to pi over 2, we have pi over 6, we have pi over 4, and we have pi over 3. Right? These are all values that are less than pi over 2, so we're trending towards pi over 2 from the left. Okay, so those are values we might think about plugging in. Well, remember then, and now you can think about the unit circle a bit, these are all values in quadrant 1. Pi over 2 is actually on the y-axis, so these 3 are values in quadrant 1. Well, if you plug in a value to quadrant 1 for sine of x, you're going to get a positive value back. Cosine of x is also positive in quadrant 1. So we know we're getting positive numbers. But what happens to these things as we move towards pi over 2? Well, sine of pi over 2 is 1. Cosine of pi over 2 is 0. So we can't plug pi over 2 in directly. So what we realize is that sine of x values are trending towards 1. Cosine of x values are trending towards 0. So remember, when that happens, this real number over 0 situation, or non-zero number over 0, we're trending towards infinity. And in this case, since both these numbers are positive, we're trending towards 0 from the right. In the case of cosine, since all the numbers leading up to it are positive, we know that we have a limit of infinity there. So as we approach pi over 2 from the left, we are approaching positive infinity with tangent of x. Similarly, if we approach pi over 2 from the right, well, if I extend the number line, I can come up with some values that might help with that. And this isn't really part of the solution. It's just something to help us think it through. Maybe we start at pi, right? And then we're working our way back to pi over 2. Remember the angles from there. This might be a little trickier to see, but there's 5 pi over 6. And then there's 3 pi over 4. And there's also 2 pi over 3, right? And you just have to think of the angles that are in the second quadrant. And now at these angles, we're moving back towards pi over 2 from its right side, or from the plus side of it, right? So in this case, sine of x is still positive in quadrant 2, right? So this one was quadrant 1. This is quadrant 2. But the cosine of x, remember, is negative in quadrant 2. Okay, so sine's positive, cosine's negative. So we have positive over negative, with cosine values trending towards 0, but being negative on their way. Sine values trending towards 1 and being positive. So we have a positive over negative as we approach 0, so this becomes a negative infinity. Okay. And then lastly, maybe you look at a graph of this function, or you can use this information to help sketch a graph of tangent of x, maybe with a couple evaluations at some of these special angles. But you remember then that the graph of tangent looks something like this. Here's pi over 2. Remember this cycle that is at the negative pi over 2? It is at the, or close to the origin here, is called its principal cycle. It's its main cycle. Those numbers should, that I just hashed out on the x-axis, should look a little bit more symmetric. One's a little further left than the one on the right, so I didn't mean to do that. It's just a hand drawing. Remember, tangent of 0 is 0, sine of 0 is 0, and cosine of 0 is 1. So I know that tangent of 0 is this ugly point I just put in right here. Now let's see what this thing tells us. We have this cycle, We know that as we approach pi over 2 from the left, we have positive infinity. So that reminds me then that this function looks like this as we approach pi over 2 from the left. As we approach pi over 2 from the right, well, I know my function does something like this. So I know we know more about the tangent of x, but right now, what we just put together regarding these vertical asymptotes is at least a sketch of what it does at its vertical asymptotes. Remember, this function here actually intersects at pi because sine of pi is 0 and cosine of pi is -1. And then this thing trends upward again, and there's a repeat of this pattern all along the x-axis. But nonetheless, this is a quick sketch of what the information we evaluated does. So we know that from either side of our vertical asymptotes, tangent of x either goes up or down. So that's a good use of our limit notation here. So remember, if we have a number in the numerator, a function in the numerator that trends towards a real number, a finite real number that's non-zero, and we have a number in the denominator that trends towards 0, we're being driven towards infinity, right? We're being driven towards division by 0. All you have to check is that the numbers that you're plugging in on your way to this function on the left or right side of it, whatever the analysis is, in this case, the left, you just have to check whether or not the numbers are both positive or both negative, or one's positive and negative, and what the ratio would be overall. Positive over positive is positive. In this case, this was a positive over negative, and we got a negative. So that might be the trickier part of these problems. So horizontal asymptotes. So just as we've been able to use these limits at infinity or infinite limits to assess a vertical asymptote, we can now define a horizontal asymptote as follows. If f is defined as a function on some interval from a to infinity, and then we take the limit as x goes to infinity of f of x, and that's equal to L, so some real number. This means, of course, that f of x can be made as arbitrarily close to L as we like, simply by taking x sufficiently large. In other words, plugging in a number for L that's large enough to make this happen. Well, then this is our limit at infinity is what we often call this, or the limit as x approaches infinity. So if you recall something like 1 over x, remember it does have a horizontal asymptote. Remember from algebra, this function does flatten out as x goes towards positive infinity. The function trends towards 0, with the y value 0. Same thing as we trend x towards negative infinity, the function trends towards 0 as well, just from underneath. So in both cases, the limit as x goes to positive infinity or as x goes to negative infinity, each of those are equal to 0. So that's and that forms a horizontal asymptote. So, and we'll get more into the horizontal asymptotes in a moment, but let's evaluate the limit of a function as x goes to infinity. So typically these will be rational functions. They could be some trig functions or inverse trig functions. We'll see at some point. In this case, we've got a rational function. So the first thing I might look at is this. I might, as a student, say, okay, I want to take the limit as x goes to infinity. Now remember, this is not a number that I can just plug in now, right? So, I can't say, oh, infinity is in the domain of this rational function because it's not a vertical asymptote of it. So I can just plug infinity in. Well, what does that mean? Infinity is not a real number. You can't just go plugging infinity in. If you did, you might say, okay, well, it's infinity squared over infinity squared plus 3, and it sounds nothing but childish, right? What does any of that actually mean? So what we might look at that's a little better is just use our intuition to say, well, if x values are getting larger and larger, what happens in the numerator? Well, I give it an x value that's some large number. I square that large number, I get an even larger number. So it looks like the numerator is trending off towards positive infinity. If I do the same in the bottom, I take some large x value, plug it into this function x squared plus 3, I get some large number out, right? So this one's also trending off towards infinity. So it looks like we have this ratio of infinity over infinity that's happening. And that could be a little confusing as to what's actually going to happen in this situation, right? The trick to one of these problems is the following. we look at the denominator. Take the lead term or the highest power of x, the leading term of the denominator for a rational function. In this case, this is x squared, right? So it's the degree is 2 of this bottom polynomial. So I'll take that term, 1, or that x squared, and I'm going to form 1 over x squared, and then divide that by 1 over x squared. I'm going to write a form of 1 that I'm going to multiply this expression by, this whole expression right here by. Okay, and when that happens, I have 1 over x squared times x squared, so that's a 1, right? On the denominator, I'm going to multiply 1 over x squared times x squared plus 3. So that's 1 over x squared times x squared is 1. 1 over x squared times 3 is 3 over x squared. Remember, this product, this term has to multiply by this term and this term, right? I'm distributing it across. Don't forget to do that. So now what I'm looking at is a function I can more easily evaluate the limit of. I know that the limit as x goes to infinity of 3 over x squared, this is being driven towards 0. We have larger and larger numbers in this denominator, so this thing goes to 0. In fact, in general, and we'll see this in another in a rule in a moment, but what I might write is I'll just put this thing off to the side. As x goes to infinity of 3 over x squared, I just need to convince ourselves that this thing goes to 0. Well, remember that this is 3 times the limit as x goes to infinity of 1 over x squared. And we checked, well, maybe we haven't checked, right? But we could use a table or some kind of intuition to prove to ourselves that this thing does in fact go to 0 as x goes to infinity, right? You could simply look at the graph for a quick reference, or you could set up a table real quick and convince yourself that as you put larger and larger x values into this function, 1 over x squared, you're going to approach 0. You're getting numbers that are closer and closer to 0. Maybe the easiest way to handle that. So that being the case, now we can evaluate this limit, which is the only thing that involves x in this expression that's left. Remember that the limits of constants are just those constants. So the limit as x approaches infinity of 1 is just 1. There's no x in this expression, so it just happens to be what it is as x goes to infinity. So we end up with 1 over 1 plus 0, and that's just 1 over 1. And our answer, the limit of this function, is 1. Okay, so as x approaches infinity, this function, its values approach 1. So we could do something similar for negative infinity, and we'll find that we have the same horizontal asymptote. I would invite students to do that on their own, but it's going to look very similar. Use the same trick. You arrive at this step. As x approaches negative infinity, 3 over x squared is being driven to 0, and we have 1 over 1 plus 0 again, and again, an answer of 1. So since we have a limit as x approaches infinity, so it tells me the following, right? We're not quite sure why there'd be a horizontal asymptote based on this, but think about it this way. As we trend x values out towards infinity, there's this horizontal line of y equals 1 sitting here. And for whatever reason, and I'm not sure if it comes from above or below, I could check that maybe by plugging in some values here and thinking, okay, if I plug in 1, I get 1 over 1 plus 3, so that's 1/4. Oh, sorry, that's 1 over 4/3, so that's 3/4. Is that correct? Plug in 1 over 1. No, that's 1/4. Yeah, sorry. So it looks like we're actually approaching from below, right? So this thing is trending this way for whatever reason. From below, it's trending towards y equals 1. So nonetheless, the only point I'm really trying to make here is that our horizontal asymptote tells us that the function gets closer and closer to y equals 1 as x trends out towards positive infinity. So this is actually probably an interesting function to graph. We wanted to learn a little bit more about its behavior. That would be an easy thing to do. Okay, nonetheless, let's move on and see a quick definition of a horizontal asymptote, right? So if, the function has a limit at infinity, In other words, as x goes to infinity, the function trends towards some real number on the y-axis, right? Then the line y equals L is called a horizontal asymptote. So, just like 1 over x has a limit at infinity as x approaches infinity, right? Or negative infinity. I've already pointed this out a few times. The limit's 0, right? We're putting larger and larger numbers underneath here. 1 over a very large number is a very small number. So they trend towards 0. Again, if you're not sure of that, build a table and convince yourself. Also, the graphs suggest that too, and I've been showing that several times. So now we just officially have the definition of a horizontal asymptote. We're familiar with the vertical asymptotes of this function already, plus or minus negative infinity. That was our first example in the notes. And we know that anywhere where the function is defined, so any values that are not 0, if we take that, our limits down here, so limit as x approaches 1 maybe, right? Or as x approaches e or something like that. The number e, that is, of 1 over x is just equal to 1 over a. We just get to use the substitution rule anywhere this rational function is defined. As x approaches negative infinity or positive infinity, again, we already showed that those are 0. So it looks like the function has one horizontal asymptote, and that's at the line y equals 0. So that's a very quick analysis thanks to the fact that we've already dealt with this function. So what we'll do is maybe in subsequent examples, if we take limits at infinity, we'll point out where we have horizontal asymptotes or where we don't and what they might be. So one general rule that we have, I sort of hinted at this earlier, is that if we're dealing with a rational function that looks like this, I would say it's the reciprocal of a power function, right? Or a reciprocal power function. In other words, n is some positive integer. So it's a little bit different than just a power function, but it's a little more specific. So n is some positive whole number. Then the limit as 1 over x to the n, or as x goes to infinity, of 1 over x to the n is equal to 0. Okay. So this is a really nice rule to have lying around. And again, we could prove that to ourselves either with the precise definition of a limit for infinite limits. The book might actually carry out such a proof. Or we can just convince ourselves with a table and maybe, I don't know, some value of n, just to maybe n equals 2 or n equals 10 or something like that. And we get some examples of this actually being the case. Or we can just maybe graph a few examples, 1 over x squared. As x goes to infinity, we'll know it flattens out. And if you do that for 1 over x to any positive power, then you're going to realize that they all flatten out and go towards infinity, either from above or so they go towards 0 or from below. Nonetheless, it's a really useful thing to have. It's a really useful fact to have lying around because now we can use these rules to dispatch a lot of different problems we might come across. So we're asked to find the limit as x approaches infinity of the rational function 3x squared over 2x squared minus 3x. Well, we had a similar problem to this before, right? We had something like this, x squared over x squared plus 3. So we're going to use the exact same trick, really. And again, the place that I look for the denominator's largest power of x. And in this case, again, it's an x squared. Right? This is just an x. It's a lesser power of x. So that's the dominant term, is what I'll call it. So 1 over x squared is the ratio I want to use. And I want to write it as a form of 1. So 1 over x squared divided by 1 over x squared. This is all equal to 1. I'm not changing the value of my limit in any way by multiplying by this. I'm just changing its appearance so that I can better evaluate it. This is an important step. What you're going to learn over time, and what you might remember from an algebra class, is that if the degrees match here, then the horizontal asymptote is just 3 over 2. Y equals 3 over 2, the ratio of the coefficients. Or in our case in calculus, if the degrees match, x squared and x squared, and they are the dominant terms in the numerator and denominator respectively, well, then the limit as x approaches infinity is the coefficient over the other coefficient, so 3 over 2. Now that's fine in polynomials, right? that'll be easy to do, but we won't always have polynomials lying around, or we won't always be working with polynomials. And this trick will be critical to help us figure out what's going on with a rational expression, so a ratio of two functions. So let's keep that in mind. Even though you might not need that for polynomials now, you're going to need it when there's a square root or something in one of these numerators or denominators, or both. So anyway, we multiply by 1 over x squared, top and bottom. Again, this is a form of 1. So we just are manipulating our expression, not changing its value. And 1 over x squared times 3x squared is 3. And similarly, this term multiplies by both this term and this one. So when it multiplies by 2x squared, we get 2. The x squareds cancel. When it multiplies by 3x, or negative 3x, note that only one factor of x squared cancels with this x here. So we get negative 3 over x. So we're left with a 1 over x times negative 3 still, and that's this expression. And it's pretty similar to what happened to, I believe, a 3 actually in the previous example. It was over an x. And anytime we have an expression that looks like this, well, we're coming back to this scenario now, right? Now we have this general rule we can use. The limit as x approaches infinity of 3 over x. Well, let me just manipulate it just a hair. As x approaches infinity of 3 over x is 3 times the limit as x approaches infinity of 1 over x. So in this case, we have x to a positive power of integer power, and that's x to the positive 1, right? That's understood. Just x itself is x to the 1. Well, 1 is a positive integer, so it falls under this rule. So the limit as x goes to infinity of 1 over x is in fact 0. Or we can just remember that is the limit we've been taking of that function over and over. So this term goes to 0, right? Because this is equal to 3 times 0, which is 0. So that settles it for the rest of it, right? The limit of these constants are just those constants. The limit of 3 is 3 no matter what x goes to. Same thing for 2. So you have 3 over 2 minus 0. Right, since the limit of this as x goes to infinity is 0. And we end up with 3 over 2 as our answer. So again, same trick. Get used to using that trick and don't forget it, even though you'll probably start taking shortcuts here and just saying, okay, this is just 3 halves. It's just the dominant terms match. In other words, the degrees match. So it's the ratio of those coefficients. When the functions get more difficult, you'll have to use this to help you through. So don't forget that that is there. And I choose this term by picking the largest value, or by finding the dominant term, or the largest power of x, in the denominator. Don't choose it from the numerator. It's not as helpful to choose it from the numerator. Even though when they match in this case, we might as well have chosen it from the numerator. But we'll see a different case shortly. So evaluate the limit as x approaches infinity of the cosine of 1 over x. Okay, so it's getting a little more complicated. We have a trig function composed with a reciprocal function, or a rational function. So what we want to do is probably work within this. Remember that cosine is continuous from our continuity section previous to this. So we know that the limit of cosine of something is equal to cosine of the limit of whatever's in the argument, right? Since cosine is continuous, we have that nice trick. And this is, I'll get back to the line above in a moment. This is that trick in action. The limit as x approaches infinity of cosine of 1 over x. Since cosine's continuous everywhere for all real numbers, as long as this limit exists and is not some infinite number, right? Then I can take cosine of the limit of this function, 1 over x. So in other words, you see how the limit just passes outside cosine, inside cosine's argument. Okay, so now I can take cosine of the limit as x approaches infinity of 1 over x. Now all that is provided that this limit is equal to some real number. And in this case, it happens to work out. If you arrive at this point, and then you do this assessment up here, which I happened to do first just because I wanted to check that if I did this, I was going to get a real number. And in fact, we remember that as x approaches infinity, 1 over x is 1 over x approaches 0, or the limit as x approaches infinity of 1 over x is equal to 0. So nonetheless, that's a real number. So when I pass this through, I know that it's going to work out for me. So I can plug 0, which is this function's limit as x approaches infinity, into cosine. So cosine of 0, we just have to remember from trig, is equal to 1. So the limit as x approaches infinity of cosine of 1 over x is just 1. So yeah, we work from the inside to the outside, provided that the limit of this function on the inside exists and the outer function is defined at it. So lastly, we have infinite limits at infinity. So sometimes if you think about a polynomial in general, you'll see a whole class of functions that you have a whole class of functions that doesn't converge as x goes to infinity, right? If you think about the end behavior of polynomials, you have either odd end behavior, something going off to negative infinity and going off to positive infinity, or it could be flipped from that, right? It could look like this. You've got even behavior, right? Both finishing towards positive infinity, and you've got negative even behavior, right? They're both finishing towards negative infinity on the left or on the right. So several different cases can happen here, and these are our infinite limits at infinity, right? As we trend towards infinity, the function trends towards infinity. But we should be careful with these things, right? Let's have a look at this first example here. The limit as x approaches infinity of x cubed minus x squared. Now, it doesn't hurt to look at each term in an expression that you're taking the limit of, in a function that you're taking the limit of, but don't get carried away with that, right? So if I look at the limit as x approaches infinity of x cubed, well, that's going towards infinity, right? There are a couple different ways I could think about that. I could recall the graph of x cubed. It looks like this, right? As I move towards positive infinity to the right, the function trends upward towards positive infinity. Same thing for x squared. The limit as x goes to infinity of x squared, I also get infinity out from that. Right? Or you could build a table and convince yourself, right? Plug in larger and larger numbers for x cubed, and you get even larger numbers out, right? So that's a good way to convince yourself that each of these is running off towards positive infinity. Now, what I don't do is this. I don't say, okay, each of these limits is infinity and they're subtracted from each other. I don't say infinity minus infinity, and that's 0. That's absolutely incorrect, right? And we'll see down here that it is actually truly incorrect, right? We don't know. Infinity minus infinity is an indeterminate form. Same thing with 0 over 0. We'll learn later tricks to deal with these indeterminate form limits whenever we can't do them with these algebraic methods that we're seeing. So in this case, what we can do is the following. I look at these two terms in my limit, and I realize they have a common factor of x squared. So I factor an x squared out from both. X cubed becomes x, right? Because multiplying that by x squared, you get x cubed back. And negative x squared becomes negative 1. Because when you multiply by x squared, you get negative x squared back. Right, so now I've got this factorization, x squared times x minus 1. Now we can think about it in a better light. As x trends towards infinity, x squared also trends towards infinity. We've actually literally written that down. And it doesn't take much to realize that if as x trends towards infinity, or as the limit as x approaches infinity of x minus 1 also approaches infinity. So we have a arbitrarily large number times an arbitrarily large number. They're both positive, right? We're sending these numbers out as far as we can to the right on the number line. So the x values are getting larger and larger and positive. So both of these things are large numbers times each other as x trends to infinity. So yeah, it's growing arbitrarily large, and the limit approaches infinity. Right? Maybe again, a table might be in order to convince yourself that each of these, or even the function itself, is growing towards positive infinity. But the other way to think about it is this. This is a polynomial. It's an odd polynomial with a positive coefficient. So you could evaluate the limit in that sense. We know that its end behavior finishes up and right. Odd polynomial with positive leading term coefficient. And that's sufficient to evaluate limits of polynomials like this. In general, any polynomial, as x approaches infinity, will have either positive infinity or negative infinity as its limit. Keep that in mind. That's a nice shortcut probably for a lot of functions. So to get back to a rational function, the class of rational functions are a bit more interesting in this realm. So if I look at each of these polynomials, x is approaching infinity. The numerator then is approaching infinity, right? It's polynomial, positive infinity at that. As x approaches positive infinity, the denominator approaches infinity as well. That's a line, or in other words, another polynomial. And it finishes up and right. Right? So we have infinity over infinity. What I want to be careful of is I don't want to say that this is just 1, right? The other thing I don't want to do is this. I don't want to say, oh, the lead power of x, the lead power of x, the ratio of the coefficients is 3/2. This, in this case, the degree of the polynomials don't match. This is x squared. This is x to the first power. So the numerator degree is greater than the denominator degree. So something different happens in this case. So see how this comes about, and to understand it, we look at the denominator and use our same trick. The leading term here is x, or the leading power of x is x to the first. So I'll form 1 over x over 1 over x. My form of 1 is this reciprocal of the leading term, or the leading power of x in the denominator every time. So I multiply both the top and the bottom by this 1 over x. And remember, I'm distributing that. So I have 3x squared times 1 over x is 3x. 2 times 1 over x is just 2 over x. And then on the bottom, I have 1 over x times 2x, so I get 2. Then I have 1 over x times -5, it's -5 over x. Remember to distribute correctly. And what we arrive at is something we can more easily take the limit of. We know that this trends to 0 as x goes to infinity. This trends to 0 as x goes to infinity. This just stays as a 2. So the bottom, the denominator we see, is trending towards 2 as x trends to infinity. In other words, its limit is 2 as x goes to infinity. And well, but the numerator has a different behavior. This trends towards infinity, right? This term's going to 0, but 3x just gets larger and larger as x gets larger. So we have a value of infinity in the numerator, essentially. And if we have larger and larger numbers in the numerator, divided by something that's getting closer and closer to 2, and this is just a bit of intuition, well, then we know that overall, the limit of this function is going to get larger and larger. What I might recommend you do here is maybe do a quick table with some values. You could, if you want to convince yourself of this, but after a while you'll quit worrying about that. You'll start to get a sense of how these things come about. But you could do 3x plus 2 over x over 2 minus 5 over x, and plug in some easy values of x to evaluate and see. Maybe try 1, 10, 100, something like that. Convince yourself that this is in fact growing arbitrarily large. You could even do that for the original function. But note that if you just did that to answer the question, you would it wouldn't suffice as an evaluation of the limit. Right? Nonetheless, the tables can give us the intuition we might be looking for, even though they're not totally sufficient as an answer to a problem. So remember, the most important trick probably to come out of all of this is this finding the leading term or the leading power of x in the denominator, making a form of 1 and multiplying your rational expression by that each time to help really see why these limits are what they are. Again, for rational functions, you're going to start to learn the pattern. If the numerator degree is larger than the denominator degree, then the limit's infinity or negative infinity, depending on plus or minus signs in here. If the numerator degree is less than the denominator degree, well, you'll see that those limits are 0. Right? And if they match, you use the ratio of the coefficients. But that's for rational functions, polynomials over polynomials. That won't be for all rational expressions. When square roots show up in the numerators or denominators or both, things get a little bit more hectic. So you'll want to be able to use this trick here. So that's it for section 1.6, and that concludes chapter 1. Chapter 2 will start to talk about the derivative.